Okay, Brian Tebow here. Another take at trying to get this under 5 minutes. So we're going to play the game. We have A/B pruning algorithm turned on with 7 plies. I'm going to drop a piece in the middle, column 4, and then the AI is going to respond right away. Now, what I've noticed is my playing strategy is try to capture corners and diagonals, and that way you kind of get the multiplier of the stacked up pieces and the diagonal pieces. And what I've noticed is that if you try to just reactively block the AI, it is going to just beat you pretty handily. So, what I try to do is just worry about my points, and you can see I'm starting to get beat here already, and that's going to continue, and I just kind of get my ass handed to me. So that's the game. You can set those options from the command line or for me in IntelliJ. I'm going to stop the game, run through the code here. Main just takes the command line input and fires up the game with a number of plies and the correct algorithm, feeds it into this game runner. Game runner queues off this finite state machine, which is turn state, and we have a turn, either the human or the AI. Human is going to wait for input, drop the piece in the right column, and then add the points, and then flip the turn, and now AI goes. AI triggers its algorithm, gets the right column that it wants, adds it to the board, adds its points, and goes to the next turn. So that's our game runner. The game board is essentially a node. You can think of it like that. So we have the number of columns, our board, 2D array. We can add a piece, we can copy the board, make a deep clone, and calculate the points when a user drops in a piece to a column. So let's get to the good stuff here, which is the algorithms. So MinMax, the trick to both the A/B pruning and the MinMax algo is kind of calculating which action we want to take, because that can't pass through our recursive function. So taking a cue out of the pseudocode for the book, I fired up, I kind of replicated the code of min value right here in my kickoff method. And so it just feeds in, and this allows us to track which column is the best, either 0 through 8, essentially. So for each possible column, copy the board, and then we feed it to this min value recursive function. Min value essentially does that same thing. It's the human's turn now, and it feeds it to max value, and these go back and forth recursively until this depth is met. So they copy the board, they set the turn, they make sure the turn's human, add the potential piece for the game state, and see what those possible points are. And then ultimately, once we hit either, if it's a last node, the game board is full, or we hit our required depth, we're going to return that score, and that's going to bubble up through our recursion, and then we're going to know which column we want to choose. So that's our min-max. A/B pruning, very similar. Again, it took me a minute to figure out how we wanted to do this, but same idea. We feed in 0 through 9 possible columns and keep track of that best score, and then it feeds down through the recursion. And the main difference here is we're not, for A/B pruning, we don't examine the whole game space. We keep feeding alpha and beta through our recursion, and then we find out if a value is greater than the beta, then that means we can break off and essentially prune the rest of the nodes and return this value that we found. Same thing for minimum value. If it's less than or equal to the alpha, that means we can prune, we break off, and we return that value. And this allows us to stop examining the game tree, and eventually it bubbles up, and we find out what column we need, and then that's the column that we return.